Welcome everyone to our first video on electropneumatic circuits and electropneumatics systems basically. So the aim of this new series is going to be looking at FluidSIM and the use of FluidSIM for designing electropneumatic circuits. And at the same time, we discuss important concepts in electropneumatic systems too. So if you guys are watching our videos for the first time, we have another series on pneumatic systems, basically introduction to pneumatic systems with FluidSIM. So I recommend you guys to watch those videos first because it provides the required knowledge not only for pneumatic circuits but also for the designing of electropneumatic systems. Okay, without further ado, let's focus on the content of this video and this series. So what I want to focus in this video is designing a simple electropneumatic circuit and showing you guys what is the main difference between a pneumatic circuit and an electropneumatic circuit. And I also show you what is a make switch and what is the application of lamp, and in general what is the measurement module inside basically electropneumatic part of FluidSIM. And also we will look at magnetic proximity sensors, how we can use magnetic proximity sensors to sense a specific position of piston within an actuator. So these are the main contents that I'm going to basically focus in this video. So the first circuit, as you see in here, the first circuit in here has two main components. And if you want to compare it with pneumatic circuits, we just had one circuit, right? We have one pneumatic circuit which provides the whole functionality for us, and it has the signaling elements and basically the control elements, processing elements. Everything is in that specific circuit and that single circuit. But when we are dealing with electropneumatic circuits, as the name shows, it is basically a combination of two main technologies. One of them is electrical circuits, right, and the use of electricity, and the other one is basically the technology of pneumatic systems. And with the combination of these two, we get electropneumatic circuits and basically electropneumatic systems. And we have many devices around us which work based on the concept of electropneumatic systems. And if we want to understand how those system works, we need to basically look at the components that are used inside electropneumatic circuits and gradually start designing like complex systems, right? So let's focus on this circuit to see what we have here and what is the difference of this circuit with the first circuit that I designed for pneumatic systems. So I recommend you guys to watch our very first video on pneumatic systems, in which I designed a very basic pneumatic circuit too. So as you see in here, we have this pneumatic circuit, right? And in this side we have electric circuit. So as I said, for any electropneumatic circuit that you are designing, you will have a pneumatic part, a pneumatic circuit, and an electrical circuit basically. Now let's look at this part, which is the pneumatic side of this circuit. Similar to what we have for pneumatic system, we would have basically the air supply, air service unit, and manifold. These three components, right? And then we would have a directional control valve, and that directional control valve basically provides the air from the manifold, or let's say from the air supply side, to the actuators. So what we have in here, you see like this directional control valve, which has 3 ports and 2 positions, is in normally closed condition, right? If the air supply is in here, it cannot operate until this directional control valve is in the second position, which is an open position. From there the air will pass inside this basically single acting cylinder. But the question is how we can basically actuate this directional control valve. And the answer is the form of actuation is going to be electrical actuation. So once we are looking at electropneumatic circuits, we would have a sort of electric actuation for the directional control valve, and the responsible component for making that actuation and basically energizing that actuation is solenoid, and the solenoid is located inside the electric circuit as you see in here. Right now the question is how we can start this operation and how we can shift this directional control valve to the second position. As you see here, we have a power supply, right, which is 24 volts, and we have a switch which is basically a push button switch. If you remember, in pneumatic circuits, instead of having this form of push button switch, we had directional control valve with a manual actuation, right, and the other side was a spring return. But here we have a push button switch, so which means if we have a push button switch in electrical circuit, there is no need to have a directional control valve which will basically provide this sort of functionality, right? So that is going to replace a directional control valve with a push button switch, basically with a form of manual actuation. Now we have this push button switch, right? And if I turn on this switch, right, the current, right, we would have a current that is passing through this line, and it reaches to this solenoid 1 and 1, right, and that is going to energize this solenoid 1 and 1. And once we are designing this circuit, we link it to basically to this directional control valve, which is located in the pneumatic side. And once this is energized, basically this is energized and it is linked to this one, right? This actuates the directional control valve, and the directional control valve shifts to the new position. And from there, because it is in the second position, which is an open position, right, the air can pass through this line and it gets there, and we would have the advancing of the piston inside this single acting cylinder, and this reaches to the fully advanced position, and until we have this switch in on condition, right, the system would stay and would remain in the fully advanced position. And exactly at the moment that I release the switch, this basically will return back to fully retracted position. And the question is how this retraction process can happen because of this spring return that we have here. If you release this, right, the current cannot pass through this line, right, anymore, and this is not going to be energized anymore. Therefore, this actuation in here is gone, this actuation, and we have a spring return in the right side, and that spring return shift this directional control valve to its new, like to its first position, which is a closed position, and then the air cannot pass. We would have exhausting of the air through this terminator, and the piston will return to its initial position. So here you can see what is happening, right? That is the procedure. So once I'm done with this introduction part discussing the concepts here, I'll show you guys how you can design the circuits and which module you have to use inside FluidSIM for designing this basically simple circuit. So that is the first one that we have. And as you can see, there are basically two new components, right, inside the electric circuit that we didn't discuss it in pneumatic base, right? And that is the solenoid and the push button switch that we have. And also I can say the power supply that we have 24 and 0 volt, which is basically providing the difference of potential, and from there we would have the current, right? That is a new part. So a very simple circuit which provides the same functionality as we had in our first video, the circuit that I designed in our first video. Okay, so here we saw what is a solenoid, how we can use solenoid for the actuation, electric actuation. Now let's look at another one. This circuit is basically an interesting one, and what we can see here, we have a push button switch, right? And we have the solenoid, right? And if you look at the pneumatic side, we have like the electric actuation, as you can see, and we have a spring return and manual override. The manual override generally is used, let's say we don't have the electrical power anymore, right? We should have a sort of manual override to basically control the directional control valve manually if we don't have the electrical power supply, right? And so that is the directional control valve. But if you look in here in the branch number 2 and branch number 3, you see we have 1S1 and 1S2, and these are make switches, which means these switches can be linked to a specific position, and if we reach to that specific position, these are going to be turned on, and once they're on, whatever we have in that line of the circuit will be energized. If it is a lamp, they are going to be turned on. If it is a proximity sensors, that is the same thing. If it is a solenoid or relay, they would have the power needed in order to do the next step, right? And we have the same thing for 1S1 and 1S2. And if you remember, when I was talking about displacement step diagram, right, and the sequences that we have in pneumatic based systems, you can watch our video on displacement step diagram and sequences. And if you look at those videos, we were using labeling and mechanical actuation, right? We had mechanical actuation for directional control valve, and those directional control valve were linked to the position of piston, right, inside single or double acting cylinder. And here, instead of having those directional control valve with mechanical actuation, we have 1S1 and 1S2, which are the make switches, and these make switches are connected to the position of piston, as you see in here, in order to sense those positions. So I'm going to design this circuit too and how the system functions, and I'll show you how we can find these components, how we can link them, and what is the functionality of each components that we have here. And if we look at this specific circuit, and once it is designed, we start the simulation. So as basically this make switch is linked to fully retracted position of this single acting cylinder, sorry, this lamp L1 is in on condition, right? That is sensing that position, right? And because of that sensing, this lamp is on. Because this is going to be closed, current can pass, we would have lamp L1 in on condition. Now, if we push this S1, right, as you see in here, current can pass and it reaches to 1M1. 1M1 is going to be energized, and as you see here, right, this is going to be shifted to the second position. Air will pass, right, and it gets inside this cylinder, and this piston moves towards fully advanced position. Now we are in fully advanced position, 1S2, and until we have this switch in on condition, right, what will happen is 1S2 is going to be in on condition. At the moment that we release this S1, the system, this spring, right, will return this directional control valve to its first position, and this air will be exhausted. Therefore, we would have 1S2 returning to its initial position, and this is going to be closed again, current will pass, and L1 is going to be on. I'll design this circuit inside FluidSIM, and I'll show you guys how this system works. Okay, so let's look at the third one. We looked at make switches, and we saw, okay, we can link it, right, to basically the position of piston, right, and also it can be linked to a relay if we have a relay within the system. I'll design some circuits in future in which we see relays and how they can communicate with make switches. But here we are using magnetic proximity sensors. So I'm not going to discuss the functionality of magnetic proximity sensors, but as the name shows, it works based on magnetic induction. And what we have in here, we have 1B1 and 1B2, right? This side, and we have a double acting cylinder. So this side, as you know, is the pneumatic side, and you can see we have now, instead of having one electric actuation, we have electric actuation from both sides, which is 1M1 and 1M2, and these are linked to two solenoids that we have, right? And these two solenoids are connected to two switches, and whenever we turn on any of these switches, these are going to be energized, and from there we would have the corresponding actuation, right? And now the question is how we put these components, specifically magnetic proximity sensors. So as you look at this double acting cylinder here, right, we have 1B1, which is basically showing the initial position for us, fully retracted position, right? And it is linked to a magnetic proximity sensor, and that proximity sensor is linked to a lamp, right? Whenever we feel that position, this proximity sensor is feeling that position, right? This lamp is going to be on, and the same thing is happening for 1B2. If we want to see how this system operates, right, we have to look here. So at the initial position, because we are in fully retracted position, we won't have any actuation right now, right? As you see, there is no actuation. But if I push this button, this switch, the first thing is, like, if I push this, 1M1 is going to be energized. This is going to be shifted to the second position. Air will pass through this arrow and then this line, getting inside this double acting cylinder, and the pressure builds up the force needed for pushing this piston towards fully advanced position, and it reaches to the fully advanced position. Once it is in that specific position, the second magnetic proximity sensor is going to feed that, right? And this lamp is going to be on, and it stays there until we push the second switch, S2. And once we push this one, right, 1M2 is going to be energized, and therefore this is going to be shifted, this directional control valve, to its initial position, and air will be exhausted through the terminator that we have in there. So with the use of magnetic proximity sensor or any other type of proximity sensors, we can sense the position, right, and we can use them for the systems in which we need a sort of sequence, right? In pneumatic base, we were using mechanical form of actuations, and those actuation components were linked to the position of piston. But there was a few issues there, right? One is the signal overlapping conditions, and because of that signal overlapping conditions, we were using roller lever valve with idle return, and the use of that was resulting in some sort of inaccuracy in correct measurement of the specific position, right? And you can watch those videos too if you want to see how those sort of connection works. But with the use of magnetic proximity sensors, we can exactly feel the position. We can exactly and accurately, basically, feel the position of piston when it reaches to a designated location. Okay, so these are the three circuits that I want to design, and we'll see how these components help us in order to have a certain functionality. So and in this series, in the next videos, I'm going to show you some applications. So okay, we designed this circuit, right? There we can see the application of this circuit and how these are used in different industrial applications. So that is going to be one of the main output of these series, and after watching these series, you should be able to see some components around yourself that are working based on electropneumatic concepts, and you know how those circuits work based on the components that we have inside electropneumatic circuits. Okay, so I'm done with the introduction part. In the next part of this video, I'm going to design each of these three circuits that I showed you guys, and you will be fully comfortable after watching this video for designing simple electropneumatic circuits. Okay, we saw three electropneumatic circuits and different components needed for designing electropneumatic circuits. In this part of the video, I'm going to design those three circuits and we'll see how they function inside FluidSIM. So in our previous series, we basically covered pneumatic systems, right, in pneumatic series, and we looked at different sub modules that we have inside pneumatic side, right, this one. Now we are going to use the pneumatic module in combination with electrical controllers, in which we have the components needed for designing electropneumatic circuits. So the first circuit that we had, let's start the first one. We had a very simple circuit in which we had a pneumatic part, right, with a single acting cylinder, directional control valve, which was electrically actuated, right, and we had manifold, air service unit, and air supply. And in the electric circuit part, we had electrical components like the power part, and we had a switch, right, and we had basically a solenoid. So I'm going to design first the pneumatic side. So for the pneumatic side, we need an actuator, which was a single acting cylinder, right? And then we need to have the supply elements, right? The compressed air supply, the air service unit for the filtration of the air and regulation and this kind of stuff, right? And we need to have a manifold. So these are the main components needed for designing this one. And in the middle, we need to have a directional control valve, which is going to be configurable one. So I'm going to choose the directional control valve, configurable one, the one which has 3 ports, right, and 2 positions. And then inside that, I'm going to choose configure valve. That is going to be, I'm going to put a manual override, and I'm also going to put electrical actuation, which is the symbol, and the other side is going to be a spring return, and hit OK, right? So that is the part that we need for directional control valve and configuring that one. And then we would have the connection to the manifold, and this is going to be the exhaust. Hit OK, and these parts should be connected too, right? And this is going to be the very last part that we have, right? And one important thing is labeling. Anytime that I design the circuit, I'll put the labels too. So I'm going to call this one 0Z. This is going to be 1Z. Here we would have 1V1, and this one is going to be 1A, right? All labels are set, and we have every components needed for the pneumatic side. Now it's time to look at pneumatic side, for electrical side basically. So what we have there is basically the power supply first. So I'm going to bring this 24 volt and then extending it a bit, and then the other one is going to be the 0 voltage, right? And doing the same thing for this one, extending it a bit, right? Now the next thing is bringing the switches that we need here. So if we go to manually operated, I'm going to choose push button. So one thing that you can do is using the D10 switch, which is going to hold the position that you apply there, right? So let's do that. I'm going to bring the D10th one for this specific switch. And we have the D10 switch, right? And we need to bring a solenoid too, and the solenoid is located inside relays. So I'm going to bring this solenoid and then connecting it here this side and connecting the other side, right? And going to call this one S1. Hit OK, and this is going to be called 1M1, and again hit OK. And now we have the electric circuit ready, and the question is, okay, we have electric circuit ready, pneumatic circuit ready, what is next? These are two separate circuits right now, right? And we need to somehow hybrid them. And in order to hybrid them, we just need to look at the electrical actuation that we have here, right? If we click here, we can choose 1M1, and then they are linked, and hit OK. Now we have the circuit ready. If I start the simulation, right, and if I push this button, current will pass, right, and this is energized, this is shifted to the second position, air will pass in here, this is going to be in fully advanced position as it is a D10 switch until I release it, right? Once I release it, this spring will push this towards the initial position. And we would have a fast retraction as you saw. Let's see it again, and then another time. Okay, so that is the first circuit that we saw in the introduction part, and what we can learn out of it is using the switches as you saw here for switch S1 and 1M1, and here we have the connection and communication between the electric circuit and pneumatic circuit. The second circuit that we had was basically connecting the position of piston, right, to two make switches, and we had a sort of measurement there, right? With the lamp we could understand what is the current position of the piston, right? And as we have designated location and we know, okay, we should stay in that specific position, based on that specific position, these lamps are going to be on condition, right? So that is a kind of measurement. So in order to design that circuit, we need to use make switch, and make switch can be connected to that specific position. But before that, we should label those positions inside single acting cylinder. So that is what I'm going to do here. I'm going to label two positions and calling them, let's say, I'm going to call this 1S1 and that is going to be the starting position for me, or I can call it 1S2, let's say 1S2, and I'm going to call this one 1S3 and calling this one the maximum stroke that we have for this single acting cylinder is 50 millimeters. You can basically adjust it based on your application, right, and based on the single acting these cylinders that you want to use for your application. So I'm going to put the fully advanced position, which is going to be 50 millimeter, and hit OK. Now we have those labels needed. The next step is bringing the make switches, and those make switches are going to be linked to these two positions. So the make switches are located inside switches, and you can find it inside general switch. So this is the first one that I have, and then that is the second one needed for designing this specific circuit, right? So bring it a little bit to the left and up, and then we need two lamps, right? And lamps are located in measuring instrument. This is the lamp, right? This is the first one, and this is the second one. And the next step is just connecting them, right? This is the second branch connected, and we would have the same thing in this side and the same thing in this side. Okay, now I'm going to call, basically these are make switches, right? We can link them to the specific position, as you can see here, and I can choose this, right? It is going to be, the first one is going to be linked to the fully retracted position. I'm going to choose 1s2, and it looks at predefined value of 1s2 state. So if we are in that state, it is going to sense that position, and this lamp is going to be in on condition. Hit OK, which means we are current. You see this arrow, which means we are currently in that state. And then this is going to be connected to 1s3, right? Hit OK, and linked. You see here, predefined variable is going to be 1s3 state. Hit OK, and then the next step is labeling these two lamps. So here you can also choose the color that you want. The default color is yellow. I'm going to choose red for this one. Hit OK, and calling this one L1. And for this one, I'm going to use L2, and the same color as the default one, and hit OK. Now if I start the simulation, you see, because we are currently in the fully retracted position, this make switch is looking at that specific state, right? And it is going to be on because we are meeting that state. Therefore, this lamp is going to be in on condition. And if I push this button, right, the system advances, reaches to the fully retracted position. And once it reaches to fully advanced position, and once we are in that specific location, this make switch is going to be closed. Therefore, current will pass, and lamp L2 is going to be in on condition. So the big difference here with the previous circuit that we designed is the use of make switches and linking them to the position of single acting cylinder, as you see here. Okay, so this is the second circuit. For the third one, we should adjust the pneumatic side too. So let me stop the simulation. I have to change this one, right? And I have to change this single acting cylinder too. I'm going to choose the actuators, the double acting cylinder from here, right? And I need a directional control valve with 5 ports and 2 positions, and these are going to be connected here, right? And then this is going to be connected. The middle one is going to be connected here, and the other one is going to be a terminator, basically, right? Let me connect it again, and these are going to be the terminator that we have. The first one and the second one, and hit OK, right? And we have to configure this. I'm going to put the manual override 2, the manual override, and then electric actuation, and it should be pilot 1. And the same thing here, right? Pilot, and we can put the manual override 2 if you want, and hit OK. Or just one side should be fine. So I'm going to remove the second override that I put there. So that side is going to be this electrical actuation. Hit OK. Now we have almost everything set in this side. The only remaining part is putting the labels, calling this one 1v1, right? And the other thing that we have to do is putting the name of 1A here. And if you remember, in the circuit that we looked, there was 2 specific labels called 1B1 and 1B2, and those specific labels are going to be linked to two magnetic proximity sensors. So I'm going to add those labels here too. Trading labels. Here I'm going to put 1B1, and because the maximum stroke that we have in the default version of double acting cylinder is 100 millimeters, right? The starting position is going to be 0, fully advanced position is going to be 100 millimeters, and then hit OK, right? Now we have the piston set, right? And we have to look at the electrical side. So for the electrical side, I'm going to remove whatever we had so far for this component. So this is going to be remove this lamp basically, and you would have the same thing here, right? This is removed, this is removed, and what we need is bringing two magnetic proximity sensors, and proximity sensors are located, let me just look at here, the magnetic proximity sensors are located in the measuring instruments, right? And this is basically that one, right? Bringing the magnetic proximity sensors here, already linked. And what else? I'm just going to move a bit these dots that we already have, right? And bringing another magnetic proximity sensor here, right? And now we have two magnetic proximity sensors, and if you remember, there were two lamps too, right? One of them is going to be linked to the first one, so I'm going to link it here and link it here, and there is another lamp that we need to bring, right? And connect it here. And I need to bring I need to add basically another mix switch here, right? So I forgot to put that one, so just let me move it a bit. Moving a bit to the left and opening a spot for the second switch that we need. So the second switch, the same thing that we did, we need to bring it from the manually operated, and I'm going to bring a push button here. And I have to change this one. We can use the detent one, but we have to be very careful about the case of signal overlapping. I will have a video on signal overlapping on magnetic proximity sensors, on in electropneumatic circuits, and we see how we can avoid these conditions inside electropneumatic circuits too. So we need to bring this one here, and this is going to be called 1M2, linking here, right? And then linking it here. Okay, so we have all branches set. This is going to be called one, I'm going to call it S1, and the second one is going to be called S2, and connecting this side here. Now we have electric circuit ready, the pneumatic circuit ready, but we don't have the hybridization cases, neither for the piston, right, and nor for the basically actuation of the directional control valve. So the first thing that I'm going to do is the actuation of directional control valve. This side is going to be connected to 1M1, and the right side is going to be connected to 1M2, right? And for this one, we have to link like this. The first magnetic proximity sensor would feel the position of piston when it is fully retracted. So I'm going to put 1B1 here and hit OK. And calling this lamp L1, would use this, the default color of yellow, and then this side is going to be called 1B2, and hit OK. This is going to be called L2, it says, so sorry, it should be L1, I made a mistake there, L1, and that is going to be called L2, right? So if I move it a bit to the left now, okay, the next step is just turning on the system, right? Just playing the simulation to see what is happening. So the first magnetic proximity sensor is feeling fully retracted position. It currently is in fully retracted position, right? This lamp is going to be on. Now if I push switch S1, if you want to review, what is going to happen is 1 and 1 is going to be energized, right? And once it is energized, this is going to be shifted to the second position. Air will pass to here, it builds up the force, and then that is going to move towards 1B2, and it reaches to 1B2. This lamp is going to be, this basically proximity sensor sense that position, and this is going to be in on condition. Let's see. So I'm going to push this button, right? It reaches to 1B2, lamp L2 is on, as you see here, right? Now if I push this one, we would have the retraction process, because 1M2 is going to be energized. This is going to basically push the directional control valve to its initial position. So let's see that. You see, completely coming back to fully retracted position once I push this one. Let's look at it again. Reaching to fully advanced position, this lamp is going to be on, and then the same thing here. So with the use of magnetic proximity sensor, we can basically sense the positions, right? And if we want to use it for sequences, we can easily combine it inside the circuits and implement it, right? Okay, these are the 3 circuits that I discussed in the introduction part of the video. In the next video of this electropneumatic circuit and electropneumatic videos, I'm going to look at OR and AND logic inside electropneumatic circuits, and I'll show you what are the main differences with pneumatic circuits and how we can have OR and AND logic inside electropneumatic circuits.